represent that in this way, and this is not complicated at all. This is very simple. But look what this shows. It shows that something is in one set if and only if it's in the other set. So it actually proves both directions. That this is a subset of that and the other way around. It shows that the two sets have the same elements, so therefore they must be equal. So you can just say, okay, conclusion. And that's all the proof, right? Where do we use the fact that x is not empty set? Well, if x is empty set, intersection x is not defined.
Sorry?
Yeah.
Could you please explain the last if and only if?
This one.
Yes.
So, what does this say? It says that y is an element of power set of b, right? For every b. So each b has its own power set. And y is in each of those power sets. So if I take all these power sets and I intersect them, it will have a y sign. Because this says y is a common element to all the power sets. But then it's the same as to say that it's the element of the intersection. Now that we discussed how to do it using trivial things, let me show you how to do it using non-trivial things, which will make us get stuck. And that's how very often I see students get stuck when they try to solve problems like this on the test. Here is a typical proof. All of these are equally not good. Okay, so here's a typical proof. Power set of intersection of x equals the set of all s's that are subsets of the intersection of x. That equals the set of all s's such that for every small s, s is in s implies s is in the intersection x. Equals all s's such that for every s is an element of s implies for every b, for every x in x, actually like this, for every x, x is an element of x implies s is an element of x. And now we're in this line, and we're thinking what to do next, and we're stuck because we don't see what to do. Already it's a mess. Okay, we could compute the left-hand side. By the definition of intersection, this is the set of all the let's call them s's because we eventually want them to be equal. So all the s's such that for every x is in x implies that s is an element of power set of x. Then we've got this. Here we have s as a subset of x. Then here we have for every element in s, let's say every t is in s implies t is in x. Now, this statement, this formula, if I bring this down under the quantifier, and also the same thing here. And that formula, these two, will then actually be exactly these two formulas. This one and the other one. Okay, so in this case, it was possible. But don't you agree with me that the fact that now this is the same as this is less trivial? Because we are kind of bringing down all the heavy notation along, whereas here we are kind of dropping. So if the difference between these two proofs is that in this proof, every next line is longer than the previous one. Whereas here, they are all the same size. Well, it is a little bit because we have this A being element of Y and the subscript and that. But also that I did from the point of view of making things trivial. So that philosophy was applying that as well. Yes?
So if it comes to a proof question, do you not get full marks if we don't reduce it to this stepwise universal quantified thing, but if we wrote it out a bunch of words?
It doesn't matter how you prove something. What I'm trying to show you here is what would be the approach that will actually get you to prove something. Because this can get very overwhelming. And this can often also get very overwhelming. Okay, so what principles did I apply? I applied the principle of working from outside to inside, applying definitions and decomposing things. But then also, after I get a feeling that maybe while I've made some progress, what I've got is too complicated, I've tried to rewrite it in a simpler way. So always I'm aiming at keeping things simple. But at the same time, being careful. I was very careful, like with changing symbols and everything. At each step, I was extremely careful not to introduce an error. Yes?
So, in this proof here, isn't it the same as what we did up there, but just with less words?
This one?
Yeah, because we just said, okay, we broke down what was written in the previous step.
Yes.
Down, which is essentially what we did up there.
Also what we did here, isn't it?
Yeah, but like, so, is there a difference between doing the one on top and the one to the right?
There is methodological difference. So this has more symbols, and it gets less trivial for our brain to process what's happening. I was kind of clever here and used the same S, but I might have ended up using different variables. So then imagine this expression would have had all different variables from these ones. Then it would have been even more difficult to notice that they're actually the same. So because when we work out something in mathematics, we do rely on our brain a little bit, right? And so it's important to keep things simple so that our brain can easily notice patterns and suggest to us when two things are the same or not. This technique of mathematics, of making things trivial, is a very powerful technique. I mean, this is the same technique with which we managed to fly satellites into space, and all the technological applications of mathematics. We are able to predict what's going to happen to something if we let it run with initial conditions being given data. Why does it all work? Why do planes fly? Why does electricity most of the time work? Because all these actions have been taken by predetermined mathematical calculations, where in a mathematical calculation you trivialize things and then you kind of gives you certainty that it's going to work, and then it does work. And if you make a little mistake, then it's not going to work and it's going to crash. So it's a very powerful technique. if using this technique you can fly a spaceship to the moon, then surely you can solve problems in the set theory nodes in the third term of second year foundations. Okay, so this is for this video. I'm going to turn it off now.